I'm just starting the recording, so go
Okay.
ahead now.
All right. Okay, so I'd like to thank the organizers for having me, especially since I did say that I'm not a geometer, nor a topologist, but I still really want to give this talk. And in particular, the reason why I really want to give this talk is because I want to actually advertise a symposium that I'm running in about a month's time from now. And so basically, the recent developments have shown a lot of connection between triangulated categories. Don't worry too much about that if you don't know what that means. And the theory of surfaces. And in particular, I came from knowing more about the triangulated category stuff rather than the theory of surfaces stuff. And my research really lies on that part of the area. And there's a lot of disconnections which I don't really understand many of this connection between them, and which is why I really wanted to run this symposium so that I can actually learn from you guys, which are geometers and topologists. So be able to learn some of these connections from you. And also, I do like to mention that don't worry too much if you don't actually know anything about triangulated categories. This is actually a 4 weeks long workshop, which means that the first week in particular will actually work on covering the backgrounds, the homological algebraic backgrounds, and what for example, what a triangulated category is, so on and so forth. So we'll start from the basics in terms of the triangulated category stuff. So you actually get to learn some of those as well. So if you're interested, please do sign up. And if you're not interested, please also try and sign up and come along and see if it actually suits your taste. So what I'll do is I'll just send the link in the chat. And the registration is basically just this page that I've put up here, and it's just right down towards the end. And you can see some of the structures there. So the reason why it's 4 weeks long is also because I don't really want it to be too intense. Every week we'll probably only have 2, maximum 3 talks, so that we can actually have more time doing some self-reading as well. And throughout the whole workshop, we'll also prepare some exercises and a forum where we can actually discuss and learn from each other. Okay. All right. So that's for the advertisement part. And this is really just the general analogy that you would expect to see in these kind of theories as well. So basically, in the theory of surfaces, every time when you're given a simple closed curve, there should really be some sort of corresponding objects in the triangulated category. And for example, if you want to compute the intersection numbers, it really is just computing some sort of dimension in the Hom spaces on the categories, so on and so forth. Even metrics, length of curves, and in particular, entropy, which is the one that I'll be talking a little bit more today, also have some sort of categorical analog. All right. So the title of my talk is going to be some subgroups of braid groups, their dynamics, and some mysterious symmetry of curves, which I really don't understand. And really, what this means is that, well, I saw this kind of situation happening in the triangulated category, but I really can't tell what's going on the topological side of stuff. So in this talk, I really won't say anything at all about the triangulated category stuff. And in particular, whatever that I claim today really is just coming from the results from the triangulated category analog. So I'm a representation theorist again, or at least I want to be. And in particular, take the claims that I'm going to make today with a really open mind. So it's probably true in the sense that because the categorical analog is true, but maybe it requires a little bit more fixing and requires a little bit to put in the right words or the right conditions into it to actually make it correct. All right. So I'll start this talk with talking about the groups that I actually care about. So the groups that I actually care about are called a class of groups which are called the generalized braid groups, or if you like, some people are also calls it the art and tits group. And in particular, the braid groups is one of them. So for a braid group, so just to remind you, the relation, if I want to give its group presentation, it basically has n of these generators here. And each of these generators is basically just a twist. For example, D1 is really just a twist that looks like this. And we have this braiding relation that's going on for the relations part. Okay, so that's the presentation that we can give for the braid groups. And usually for us, which are algebraics, we usually call it the braid group, which are associated to what we call the type A graph, meaning for each of these vertex here, you have a generator. And every time when you have an edge connecting between them, they braid. And in particular, you can kind of think of this as like a braiding relation, which is 3 times, which we usually don't write. So meaning we have di dj di is equal to dj di dj, something like that. And usually this kind of the braid groups, there's also a corresponding Cochlear group, which is just saying that, well, let's put in the extra relations such that they are actually self-reflecting or self-inverse, and you get what is called the Cochlear group. So these are usually finite groups for some nice cases. And in particular for the braid group case, the corresponding Cochlear groups are just a symmetric group. So you can really think of this as like, topologically, the braid groups kind of have two strands lying around, and then now you project it onto a plane and you kind of kill the topology of it. And that's how you get the symmetric group. Okay, so that's the braid group. So you would hope that the generalized braid groups actually contain the braid group. And there are also other types of generalized braid groups. So the one that I'm really going to focus on today are what we call the rank 2 braid groups, meaning they correspond to the graph that looks something like this. So again, there are two generators. So 1 and 2 generators here. And instead of braiding 3 times, we call this the n braiding relation, meaning instead of having sigma 1, sigma 2, sigma 1 equal to sigma 2, sigma 1, sigma 2, we have this n braiding relation right here. So we have them alternating n times on one side, and so is the other side. Okay, and so what these braid groups are, well, it's kind of hard to tell just from these conditions, but the Cochlear groups are actually quite well understood. Meaning, if I now add in the two relation, which is again the self-inverse relation here, these are well known. These are basically the dihedral group, or if you like, they are basically the symmetry of n-gons. So when n equals to 3, you have the symmetry of the triangle, which is just the symmetric group of 3 elements. And if you have n equals to 4, it's just the symmetry group of the square. N equals to 5, you just have symmetry group of the 5. All right. And understanding these braid groups turns out to be much harder than the Cochlear group itself. In particular, they're no longer finite. And it's kind of surprising to many people how much we know about the Cochlear groups, but almost nothing about the braid groups. Okay, so one of the goals to actually understand these generalized braid group is to use one of the properties, well-known properties about braid groups that we know, meaning the braid group is a mapping class group. And just to quickly remind everyone what a mapping class group is, it's just a group of diffeomorphism quotienting up by the isotropies fixing boundaries. Okay, and so one way to try and understand these groups is to hopefully understand them as some sort of subgroups, in particular nice subgroups of mapping class groups. And in this, the reason why we would like to do this is that, well, now we can actually look at this action on the simple closed curves on this corresponding surface, and we can obtain what is well known as the Nielsen-Thurston classification. All right, and the Nielsen-Thurston classification basically says something like, given any braid element in a braid group, which is the mapping class group of the n-punctured disk, every element is either periodic, reducible, or pseudo-Nosov. And I'm not going to give the correct definition of what periodic, reducible, and pseudo-Nosov mean, but I'll just kind of explain them in terms of what happens to curves when you look at the action on simple closed curves. So in particular, when we say that a braid is periodic, it means that if you take any simple closed curve that you like embedded on the disk with n punctures, some power of it acts as the identity. So again, just so that there's more pictures for us to actually think about stuff. So we usually think of the braid this way, and you can think of it as a mapping class group action by just putting two sheets of these disk here and thinking of the braid as like the time of how everything transformed going downwards. Okay, and in particular, basically what this means is that the first braid, the first generator of the braid is going to take a Dane twist around this first two punctures here, and the second generator is going to take the Dane twist around the last two punctures on the other hand. All right, and usually, just for convention purposes, I usually take my braid generators to turn counterclockwise instead. And for a periodic braid, one example is that you can consider the Dane twist, which is given by this whole big circle here, and you take the half twist of it. Okay, or if you take the full twist, then it's just going to be the identity on any simple closed curve. And if you take just the half twist of it, it's actually given by this braid right here. So in terms of the generators, it's just D2, D1, D2, meaning you do D2 first, and then do D1, and then do D2 again. And it turns out this is just a half twist on any simple closed curve. And so basically you will get something like this. And if you do it again, it just goes back to the same curve again. And this actually happens for any curve that you like. Any embedded curves in the surface is gonna have such a property. And we say that a braid is actually reducible if it acts as the identity on some curve, but not all the simple closed curve. So again, in particular, if we look at the braid, which is generated, sorry, the braid element D2, which basically just twists this part here, we can see that it doesn't change the straight line curve there, but the curve, but the arc, this arc curve here actually gets twisted in another way. All right? Okay. Are we all happy? All right. So for reducible curves, some curves need to be acted as the identity, and some curves doesn't. All right. And finally, we get to the pseudo-norms of curves. So since foliation was mentioned in the first talk, I should probably give a foliation definition as well. It basically, a diffeomorphism is the pseudo-norms of diffeomorphism if you have two transversal foliation, which are you can think of them as one of the unstable foliation and one's the stable foliation, and the pseudo-norms of diffeomorphism basically scales them by some algebra in terms of their measures. And for its action on curves is basically just saying that, well, if you take any simple closed curves and you take higher and higher powers of these of that braid, it basically just makes the curve more and more complicated. So there's some sort of very well mixing condition going on, or it has high complexity, if you like. And just to give you an example, so consider this this braid here, which is given by D2 inverse and then D1. So again, it basically just says that take this one here, do a clockwise rotation, and then take this one here, do a clockwise rotation, and then take this one, this Dane twist here, and do an anti-clockwise rotation. All right. And I've drawn a few examples here. You kind of need to trust me on this, or if you want to take this back home and then try and work it out yourself. So if I do it once, it'll give me some curves that look like this. And if I do it twice, it'll give me some curves that look like this. And you can see that I've given up on drawing the last curve here. So, and what I've done here is basically telling you that, well, as for this part here, basically there's like 1, 2, 3, 4, 5 parts of this, and then 3 parts here. And basically this is just saying that there's 13 lines on the top and then 3 lines on the bottom. So basically what I'm saying is that if you squint hard enough, you squeeze these curves together, there's basically 13 on them, getting squeezed on the top part, and then 8 curves getting squeezed down the bottom part. Okay. And this turns out to be helpful in the sense that, well, although what I've drawn turns out to be a graph, or in some sense a graph rather than some simple closed curve or curves embedded on disk and counting its length, it turns out that knowing how many pieces of these is actually good enough. And good enough in the sense that you can actually compute entropy out of it. And so before that, let me just quickly say what I mean by entropy. And you should really just think of this as, up to isotopy, how does the length of the curve grow? So given a surface S and pick any metric that you like on it. And for any curve alpha, we'll just use L mu alpha to denote its length. And the topological entropy of some element in the mapping class group is based, when it is pseudo-norms of, you can compute its topological entropy by just taking this limit right here. And again, what this means is that you're looking at how the length grow as you take higher and higher powers of the diffeomorphism that represents it. Okay, and if it grows exponentially, then it gives you some sort of number, and if it doesn't grow exponentially, then it just goes to 0. Is the idea. Okay, and the way that you can try and compute these kind of entropy out of these graphs is basically, well, try and pick some nice representative of curves embedded in the disk, so that these are actually geodesic representatives, meaning within the isotopy class of curves, pick the ones that actually minimize the length in some sense. And now once you act on, you can think of these curves now as some sort of embedded graph, and then you can basically just try and transform it according to what you think, how a graph would transform. So for example, if I take this white curve here, after doing it once, it's going to get transformed to something that looks like this. So in particular, I'm getting 2 pieces at the top part and one piece at the bottom part. So as you can see, I've written it down this way and this way right here. Okay, so the white curves get transformed to 2 pieces of the white curves and 1 piece of the purple curve. All right, and if I just look at how the purple curve transform, then it basically just gives me 1 piece of the white curve and 1 piece of the purple curve after isotopy. And that's what you denote it by. So you can think of this as some sort of graph transformation, if you like, and you get this matrix which encodes the graph transformation. And to compute the entropy, because you've actually picked these to be the geodesic representative, basically what you have here is that you now have to compute this infimum right here. You can just take higher and higher powers of this matrix instead. And instead of this part here, this is wrong. This should be, you just take the length of the curve that you like to start off with. So for example, let's say that we're taking the length of this white curve here. And you just see how this length grows accordingly. And the way that it grows, because of how you can actually squeeze everything close enough to these geodesic representative, it basically grows according to this matrix. And just using some Perron-Frobenius theorem argument, you can show that this limit actually converge to the logarithm of the Perron-Frobenius eigenvalue. So meaning this eigenvalue here is, so this Perron-Frobenius number is just the top eigenvalue of this matrix, and it always exists and is always a real number. Is the theorem. Okay, and so it is a big theorem of Thurston that which shows that these pseudo-Nosov curve, this log lambda part, this lambda is actually an algebraic number. And in particular, in this case, you can see that because it's given by an eigenvalue of some matrix, it is indeed, it's basically the root of the characteristic polynomial of a matrix, therefore it must be an algebraic number. Okay, all right, so back to our goal. So our goal was to actually understand these generalized braid groups as mapping class groups. And it's actually not known, or in some sense not possible for some generalized braid groups to actually have some injective mapping, injective representation as a mapping class group, meaning they can't actually be viewed as nice subgroups of mapping class groups in some sense. But for the rank 2 cases, there is a nice way. And in particular, throughout this talk, I'll just work with 2 very specific examples. So one of them is the one with the relation that has the 4 braiding relation, and the other one is the one which has the 5 braiding relation right here. All right, and in particular, basically the way that you inject them into actual braid groups is to say that you take the first generator and you take alternating dainties that are actually commuted. Well, because they're alternating, they don't intersect with each other, they actually commute. So in particular, for example, in the case where we have the 4 braiding relation here, all you do is just you take this first generator and you send it to the dainties that's given by D1 and D3. And similarly, sigma 2 right here, you just take the dainties that's given by D2. All right, so you just twist the middle part, and the first generator twists both sides, both ends of the parts. Okay, and similarly for the braiding relation with the 5 braiding relation, you just send it to D1 and D3 for sigma 1. But for sigma 2, you actually send it to D2 and D4. So both of them are pairs of dainties. Okay, and in particular for this case where we have this 4 braiding relation, there's a lot of symmetry that's actually going on. And in particular, you can see that if I now take this rotation by pi along this center point here, this rotation actually commutes with the dainties, right? Because D2 lies exactly in the middle of this rotation, and D1 and D3 are actually just one to the other. So you can think of this as like some sort of if I take the dainties that correspond to this loop here, after the rotation, it actually gives me the loop that defines D3. And similarly, if I take the D3 loop, it goes to the D1 loop. So in particular, if I take the subgroup D1 that's generated by the dainties D1, D3, and D2, all of them commute with the rotation R. So what this means is that, well, if I now take my disk and I quotient it out by this rotation action, it gives me some sort of an annulus right here. Hopefully the picture is clear enough, because basically what I'm saying is that you're quotienting out this part, and you're identifying those 2 parts together. And so it kind of sticks together to become a disk again. But now, because of this rotation having an extra fixed point in the middle right here, we have this extra hole in the middle, if you like. And what happens now is that, well, remember that back then the dainties were just switching these 2 points halfway through. But now, once you take this point, getting up to this point here, because the 2 points are actually identified, you end up jumping back to this point, and then you just go back in again. Okay, so it becomes a full twist. So in terms of pictures, you can kind of view it as something that looks like this. Okay, so you can think of this as doing the half twist. Halfway through, you actually jump to the other side of the point already, and then you just do the other half twist again. So it becomes a full twist in that sense. And in particular, this kind of braid group, although at the start we didn't really see it as some sort of mapping class group, it turns out that this is also a mapping class group, where now it is a mapping class group of an annulus instead. And the first Dane twist, instead of doing a half twist, it now does a full twist that goes about this middle circle of the annulus. All right. Okay, so the reason why this is nice is because, well, again, because of this, a lot of this symmetry here, it tells us that when we're trying to compute these kinds of compute the entropy as what we did for the first example right there, there's a lot of symmetry that's actually going on. In particular, for example, if I take L1 and I act by this, what I claim to be a pseudo-Nosov curve, it goes to this complicated curve right here. And in particular, I'll just do the same trick again, which is just counting how many pieces that I have in each part of them if I squeeze them hard enough. And it tells me that, well, there's 2 pieces of L1, there's 4 pieces of L2, and there's 3 pieces of these L3 here. And for example, now if I want to know what happens with L3 instead, so this here is the image. So this one right here, oh, my pen is not working. Okay, this one right here is the image of this D2 square D1 D3 D3 cube acting on the curve L1. So what happens if I actually want to know what happens to L3 instead? Well, because they commute, I can actually just say that, well, if I want to know what happens to L3, I know that this L3 is just the rotation acting on L1. And because the rotation commutes with my braid, I can just do the rotation later instead. So meaning, all that I need to do is just take this purple curve that I end with, the complicated purple curve, and just rotate it. And that's what it's going to give me. And as you can see, basically, that just tells me that my L2, the number of L2 just goes back to itself because L2 is actually preserved under the rotation. But the number of pieces of L3 is going to go to the number of pieces of L1. And similarly, the number of pieces of of L1 is going to go to the number of pieces of L3. So they kind of swap instead. So in particular, the rotation actually sends L1 to L3, and it sends L2 to L2. And in particular, if I square them, I square the rotation, it goes back to the identity. Okay, so L3 goes back to L1 in particular. And what this allows me to do is that, well, instead of viewing this matrix that I ended up getting to compute the entropy, which actually has entry in Z, I can now view it instead as a module over this ring, Z adjoint R, such that I quotient out by R squared equals 1. Or if you like, this is basically just the ring that says, so this is just the same thing as saying that I want the group ring of Z mod 2Z with the coefficients in Z. And now I can actually ask, okay, so instead of computing entropy from the eigenvalue of this matrix right here, what happens if I actually compute the entropy from this matrix with coefficients in some sort of ring, some sort of other rings? And it turns out that, well, because this polynomial solution here has 2 possible cases, right? R squared equals 1 if I want to look at their solutions in Z, that it basically says that, well, R is either equals to -1 or R is equal to 1. And it turns out that all the eigenvalues of the top matrix that I had right there can be obtained from the bottom part just by looking at all the possible eigenvalues that you obtain by evaluating R, these 2 different values. And in particular, it turns out that when you evaluate R at the highest number, the highest real number, it gives you the Perron-Frobenius eigenvalue, meaning the top eigenvalue is actually captured in this R equals to 1 part. Okay, and so instead of looking at this one right here, which tells me that this is actually a rank 3, or maybe I should say, instead of rank, let me just use, it's a degree 3 algebraic number. It turns out that entropy, the log of this lambda number, this lambda part, or if you like the scaling of the foliation, is instead of a degree 3 algebraic number, it tells me that actually, if I just look at the subgroups of these that are generated by these Dane trees that are defined, or the rank 2 braid groups, if you like, they are all just degree 2 algebraic numbers. And this is actually true for for all the other examples. So in particular, this is just a particular example. And for any other examples, if you find a corresponding graph that actually helps you compute the entropy, and you look at this matrix, there is always a way to reduce it to rank 2 matrix, evaluate at R equals to 1, and that gives you, that actually helps you compute the Perron-Fabier's eigenvalue as well. So for the case where n is equal to 4, meaning this 4 braiding relation case for the rank 2 braid groups, it's still kind of obvious what you can do because there's this nice rotational symmetry that's going on. But what happens when I try to look at this 5 braiding relation instead? Well, things get kind of complicated, get a little bit more complicated, right? Because your first guess is that, well, can I actually do something like a rotation down this middle line here? Well, if I try and do such down this axis here, I should say. But now you can see that if I actually do this rotation along this point, then it doesn't actually commute with my actions anymore. Meaning I can't actually take the quotient and do some sort of a nice mapping class group analysis on it again. So there really isn't a nice obvious symmetry, and in particular, I can't really take a nice group action, quotient it out by these kind of things, and then try and look at what kind of mapping class group that you're actually acting on it. But somehow the same kind of case actually happens. So meaning instead of looking at these kind of higher dimensional matrices that actually helps you to compute the entropy, it turns out that you can always reduce it into rank 2 matrix in some sense. And again, I'll just use some sort of an example to illustrate my point here. So if I look at this 5 braiding relation case where it injects into the disk with 5 punctures, then the rate curve transformed by this braid here, which after the injection is given by this complicated expression, gets transformed into this rate curve right here. So again, if you squeeze it hard enough, it goes back to some sort of a graph that I started off with, and you can count the pieces, which tells you that, well, there's 1 piece of the red curve, 2 pieces of the green curve, 3 pieces of the orange curve, and then 2 pieces of this dark green curve right here. And again, you do the same trick, you write down the matrix, and you can now kind of ask, okay, what happens to the orange curve and the green curve, the dark green curve and the light green curve? And it turns out that there's this kind of nice, what we call the Fibonacci relation, which tells me something like there's a map, which there's an assignment, if you like, because I don't even know whether it's a map, which tells me that the red curve should go to this orange curve right here, and the dark green curve should go to this light green curve right here. And when I take the light green curve, it should send to the disjoint union of the dark green curve and the light green curve, and the orange curve should again send to the disjoint union of the red curve and the orange curve. So again, the reason why I call this the Fibonacci relation is because, well, this looks really similar to what you would have, which looks something like this matrix right here, which tells you that, well, I'm always just going to take the previous one and then plus 1 and get to the next, plus it and then get to the next one. Okay. And when I say that this relation actually holds, what I really mean is that, well, if I want to know what happens, for example, to the orange curve, I can't really tell you what happens to the whole curve itself, but in terms of each part of this graph, that I can actually just look at this relation and tell you what happens to it. Meaning, if I want to compute this part right here, all I need to do is just start with the rate curve, look at each of these components, and then just apply the relation. So for example, if I want to know what happens to the orange curve, I'll just take the rate curve, and because of this relation that tells me that the rate curve just gets sent to the orange curve, it tells me that, well, it gives me 1 piece of the orange curve. And 2 pieces of orange curve just tells me that I get 1 piece each, which gives me these 2 numbers right here. Okay, and so on and so forth for dark green curve and light green curve. And similarly, to compute the light green, what happens to the light green curve, all I need to do is just compute the dark green curve and apply the relation again. So what this means is that, again, there is a nice transformation that's happening right here, right? Given by this Fibonacci relation right here. And again, I can reduce my matrix into a matrix with entries in some other rings instead of the ring of integers, and it's given by this ring right here, which tells me exactly that delta square is equal to delta plus delta 1. Okay, so again, you can see the correspondence here, meaning if I take my dark green curve and I apply it twice, dark green curve goes to light green curve, and light green curve goes to 1 piece of dark green and 1 piece of light green. So it gives me this delta plus delta 1 relation. And you should think of this plus as the disjoint union instead in terms of the curves. So again, this is an algebraic number. In particular, is actually the golden ratio is going to be part of this solution, which is 2 cos pi over 5. And and basically it says that, well, now if I actually want to compute the entropy using this big 4x4 matrix here, I can actually just compute the entropy from this smaller matrix, but where I actually evaluate this delta as the golden ratio, again, which is just the biggest real number solution to the polynomial equation that I have. And again, this turns out to tell me that, well, instead of being a degree 4 algebraic number, it's now actually an algebraic number instead of over Z, it's actually just an algebraic number over this ring Z rather than delta. Let me just write it as Z 2 cos pi on 5, meaning Z adjoin the golden ratio, which is the biggest subring that contains the golden ratio in Z. And that's the conjecture. So in particular, in general, my claim is that, well, the entropy of these pseudo-nodes of braid for these rank 2 braids are actually just degree 2 algebraic numbers, but instead of being algebraic numbers over the integer Z, they're actually just algebraic numbers over these ring, which is just Z adjoin some sort of 2 cos pi on n numbers. And in particular, I don't really understand why this kind of symmetry should occur in part, and when it's obvious in the case when the 4 relation here, you have this extra rotational symmetry that's going on, but for all the other higher n cases, there doesn't seem to be a very obvious symmetry that's going on in this case. And in particular, I can't really explain topologically, alignment of curves really comes from a proper topological continuous map on the whole disk, which is just a rotation. But in this case, all I can do is really just kind of tell you algebraically or build it up combinatorially by just telling you that, okay, these curves should go to these curves, and some curves somehow goes to the disjoint union of 2 curves, and that should always be the case. So if you have any input into this, I would really hope to hear more about it. But other than that, thanks for listening.
Great, thanks, Ed. Are there any questions?
I have a simple question.
Yep.
So way earlier at the start, when you were talking to find the entropy, you said that it was independent of the choice of metric. Is that obvious, or is there something?
It's quite deep here.
Yeah. Okay.
So it's independent of choice of the metric, and it's also independent of choice of the curve that you start with. So, but yeah, you're right. It's not obvious.
Okay. Yeah. Thanks.
And I should also probably say that in particular, I know the proof for the triangulated category stuff, but I have no idea how to prove it for the topological stuff.
Mm.
Any more questions for Ed?
I have another question.
Mhm.
So maybe I didn't understand correctly, but towards the end, so you were talking about sort of the case with the where there was no
Five
obvious
relation.
symmetry. Yep. Yeah. Exactly. Yeah. So so is this? I guess I want to understand. Sorry if the question's not very.
I mean, look, my question wasn't really precise as well, so that's fine. So any clarification would be great.
Okay. So is the Fibonacci relation? Because you've kind of got an example here of some curve in this 5 braid relation. And in this case, it's the Fibonacci relation that gives you this reduction from the 4x4 matrix to this 2x2 one over a different ring. And so is it always the Fibonacci relation in this 5 braid relation, or is it something different in a different case?
Yes, it's actually something different. So it's actually going to be the Chebyshev polynomials in particular. So the Fibonacci relation is the one that's satisfying this polynomial relation. So it's always going to be some sort of polynomial relation, which tells you something about delta to some power n is going to be some positive sums of stuff. And if you like to look at it, it's basically called the Chebyshev polynomial. So Chebyshev polynomial.
Uh-huh.
And one more way to think about this is that basically it's the smallest algebraic polynomial which contains this number as a root, 2 cos pi on n, where the n now depends on the braiding relation n.
Oh, okay. Okay.
Yeah. So yeah. Yes. Yeah. So it's going to be the polynomial relation that comes from these roots to these kind of numbers.
Okay. And there's currently no like geometric interpretation for what symmetry this could possibly be.
At least not that I know of. And and the thing is I don't dwell within the geometric or low dimensional topology world long enough to know whether or not this has a known answer as well. So, but I kind of doubt so. Like I feel like it, because as you can see, like these curves here, this red curve here goes to this orange curve, and this dark green curve goes to this light green curve. And in particular, basically it tells you that you have sent to disjoint curve to something that actually connects in some sense at the punctures, if you like. So this in particular, this tells you that it can't really be a homeomorphism. Previously, for the rotation, it's actually a homeomorphism. In this case, it needs to be something that's actually reducing.
Okay.
So I have no idea what it should be.
Okay, thank you.
All good.
Are there any more questions for Ed?
Okay, not to be annoying, but I have one more question.
Look, I'm more than happy if you actually ask more questions. Like, I really want to know more about these stuff as well.
So in the 4 braid relation, there's like, because you've got an even number of punctures, there's, like you said, there's an obvious symmetry.
Yes.
And so I guess in the higher order, you might have like 6 punctures. Does it not generalize in the sense that it's the same, like the analogous symmetry?
That's a very good question. So for all the even cases, you can always do a rotational symmetry. So you can imagine that for the case where you have 6 punctures, the rotational symmetry reduces the matrix down into something that's size 3, for example. But it doesn't go down to size 2. And the claim is that it actually always goes down to size 2. And for all the even cases, reducing it once is the easy part. Reducing it, the next step is the one that's missing again.
Okay.
But yeah, that's a very good question.
All right. Thanks.
Okay. All good.
Great. If there aren't any more questions, let's thank Ed for his talk again.
Thank you. Thank you.
Thank you very much.
So yeah, sign up to the symposium. I'll potentially be able to explain much clearly or proving many of these statements in terms of the triangulated category case. It's quite a nice transformation on triangulated category. It's actually quite simple in some sense.
Sounds great.